right, folks, 3, 2. Welcome everybody to Lecture 7. We're talking about MIPS, and we're right in the middle of talking about how to translate C code into MIPS with decisions. C code is where you're having the branches, you're being smart about things, you're making choices, and you're standing in front of the projector. So what we have here is we have the news in the day. Connect is the new hot thing. You know, you play video games are moving around. Forget Connect. Connect is so 2011-07. What we've got here is a Microsoft and University of Washington project that uses the fact that magnetic fields are altered in very characteristic and repeatable ways if your body is in the middle of them. So imagine your refrigerator giving off a very low quality, very high quality, but very low power electric field. And when you walk by your fridge, you move some gesture, and it remembers what that gesture is and what you've mapped that gesture to be, and you're now allowed to have your hands and your body, without having any camera, because of the way the magnetic field is being interrupted in a very characteristic way, do things. So the idea is, in this demo, he kind of makes a gesture, like, hey, and makes some gesture, and then the system can know what that gesture means semantically. Pretty powerful stuff. Your body is an antenna. Powerful stuff. I always want to give a shout out to anybody watching remotely. Dr. Mario Scarzi from Italy sent me some mail, so shout out to him. And anybody else watching online, send me email, ddgarcia@cs.berkeley.edu if you're watching this webcast, and we'll give you a shout out. It's great to have some worldwide attention. In review, we've seen a couple things. We learned about how load and store were our first memory to register operations. You saw that store was a little strange because the data flow went the wrong way. That was a little bit confusing. Goes to the right rather than always going to the left. We saw how we have conditional statements, and you have a little bit of intelligence to our MIPS now for the first time ever. It's not just a dumb calculator. It actually can make some decisions by the use of branch equal and branch not equal, BEQ and BNE. We saw 5 new instructions and no new registers. So we were talking about loading and storing words, but people always come to me right after and say, but Dan, I want to store a byte and read and write a byte. Well, you're right. Your answer is, if it's load word, LW, you're going to guess, you can even just guess that it's going to be an LB for load byte and store byte, SB. Same format as load word and store word. The only details are subtle, right? It's subtle. You're only affecting a byte. So in load byte, it is saying to the system, I want to grab this particular address. Remember, always you have the base register and you have the offset. That adds together. That no longer has to be byte aligned. That can be anywhere in memory, because you're asking for 1 byte. So that can be anybody. There's nothing about multiples of 4 anymore, right? That's why I have a 3 here. S1 would be a pointer that is word aligned. Word aligned. We're talking about being word aligned. S1 is word aligned, but now the offset can be some number that's not 0 or 4 or 8 or a multiple of 4. So I'm stuffing it in S0. You're saying, well, what do you mean stuffing it in S0? S0 is 4 bytes wide. You're only grabbing 1 byte from memory. What happens to S0? This is what happens to S0. S0 has the byte always loaded, regardless of where it is in memory, always gets loaded to the lowest byte in that register. So there's your byte. But load byte assumes that you want a signed number. Okay? So a signed number is an 8-bit signed number, 2's complement. But I can't just fill these with zeros, as you might be naturally inclined to do, because it's easy just stuff zeros there, because if this number is negative, what's the x? 1. So what does this read when I just fill it with zeros in a 2's complement number? Yeah, a small positive number. That's ridiculous. That's not what I wanted. I want it to be preserved that same number, but just not stretch. I want to extend it. I want to be able to sign extend that. So what happens is I take this bit and I smear it across the left-hand side. If it happens to be a 0, then it happens to be a small positive number. If it's a negative number, that 1 smears the 1 across, and now the number is the same number it was. I don't change the value, but now I can read it as a 32-bit small number, negative number, rather than a 8-bit small negative number. It's the same number, though. Okay? So that's the key to reading bytes, what happens there. Normally, we don't want to sign extend characters. Normally, I just literally want those 8 bits and don't want to actually affect these. For the most part, it doesn't matter what you do, because you only are going to probably use these and mask these out and only care about those 8. But sometimes you actually care about thinking of this as a bigger number, and you want just 8 bits of that number, but still preserve the number thought of as a 32-bit number. So if you actually don't want this guy to be sign extended, you want it to be 0 extended, then you use LBU for an unsigned number. And that says, because it's unsigned, I have no negative numbers, right? Unsigned means 0 to some max number, therefore you just always stuff zeros at the front of it. Right? Unsigned numbers are always positive, therefore 0 filling is the right thing to do for that, and that would be just give 0 extension. Okay, questions about LB, LBU, or SB? Yes, question.
Is it possible to take 4 characters from different places and put them in one register?
Yes, it is. It's a great question. Can I take 4 characters from 4 different places? Would those 4 different places be 4 different memory locations or 4 different other registers?
Yeah, 4 different other registers.
Sure, 4 different other registers. I can do that. I haven't shown you how to do that until I think later today. Later today lecture, I'll try to do some logical operations that let you do that. Okay? But yes, the answer is you do some bit masking things. So you can take this and AND it with that and OR with that and shift it over. The answer is very easy to do. Very easy to do. Trivial. Okay. And fast to do because I'm doing register-to-register operations. So it's no speed issues at all. All right. So now let's talk about overflow. We talked about it early when we were in numbers. And now we're kind of in the number space again, loading and storing bytes and thinking about sign extension or 0 extension. So let's think about that. Just like when I have only 4 bits or a nibble to store a number, when I add 15 plus 3, obviously 15 is the biggest unsigned number I can have, therefore I can't add anything without overflowing. So 3 is going to overflow. Okay? If I have a 5-bit answer, but I actually only have a nibble, 4 bits to store it, I have overflowed. So when I do my addition and subtractions, I want to be able to tell the system to either trigger an overflow or not trigger an overflow. It turns out that some languages do care about it and some languages don't. Before I even told you what C did or not, you would know the answer. Because I'd say to you, what does C do? And you would think to yourself, C does the fastest thing always. So it's fast is to ignore any problem and just go ahead and trust that you, the programmer, know what you're doing. So C would not trigger an overflow because it's faster to just ignore it and just keep going. So C does not trigger it, but some languages do. And at that point, you are now in the curious case of needing to be at the MIPS level, but to send information back up to the language level, to Ada, who needs to trigger to the user that, hey, an overflow has happened. So that's a little bit more complicated how that happens. But for now, we'll just call it about detect, and we'll deal with that later. I think we actually never even ask you to talk about it. We don't teach you how that works. You can read about it. It's something called a trap and some other things you can read about. It's in the book to understand how the MIPS level sends messages back up to the language level. But for now, the word detect is all we're going to ask you. Can you detect or not? Does it do something and just trigger it? So detection happens with normal things. Everything I've said so far triggers that detection of an overflow. Add immediate, and subtract. These do not. Unsigned. When you hear the word unsigned, your brain, in terms of overflow, your brain should say to yourself, oh, unsigned, okay, that means only positive numbers, right? No negative numbers. And it also means don't worry about overflow because it's like the odometer wrapped around, but if you think about it as unsigned, that's a natural occurrence. You just wrap around and I know what you mean, so don't bother me with the details. I know it's going to overflow, but I don't care. I just kind of want the lowest bits. And so what this addition does, what's kind of neat, is it wraps, it might cause an overflow, it might wrap around, doesn't detect it, my overflow may happen, and what you're really storing in that lowest 32 bits in the register you have as a result of these 3 operations is the lowest 32 bits of that calculation. Look at this. If I only store the lowest 4 bits of that addition, what it's really doing is it's calculating it in 5 and throwing away everything but the lowest 4 bits. So you should be thinking about that. When you see an add IU and a sub U, it's really, okay, overflow not detected means it's doing some calculation and then invisibly for me for free, throwing away any bits higher than my 32 that I can store. Does that make sense? Okay. So now let's start with some logic operations that are useful for doing some of the calculations later. You'll see why this is useful. We kind of did this on Friday. So here's shift left logical. You can see the format looks kind of like the immediate format because I've got register, register, constant, right? And where that constant is the guy who's the amount you're shifting. But we're going to see that that's actually subtle. It actually isn't the same format as a register, register, immediate because some other details will come up. But For now, I have register, how much you're shifting by. And to shift means you pick up the bits, literally pick up the bits, you zero out what was there, and then you slide over to the left, your left, my right, and then you drop them down. So here's SLL2, which is, and here's the beautiful C code. Many of you have seen this. How many of you have seen that greater than, less than, or greater than thing? Okay, most of you have seen that before. So this is how it looks like in C, and this is what it maps to in MIPS. And the idea, if you haven't seen, for those of you who didn't raise your hand, here's the bits. Here's, I happen to have the value 2 stored in hex. So here is the 2 here. I'm essentially inserting zeros as I slide over. My model of pick it up, zero out the whole thing, and then put it down, shift it over, is like shift it over and then backfill it with a 0, is another way to think about it. So the 2 green guys are the zeros that filled in. What is the arithmetic effect that shift left does? Multiply by 2 to the some number, 2 to the shift amount, right? Pretty easy. So, and shift right logical does the same thing on the right, pushes things to the right, and 0 fills it. Does that make sense for things that are signed? What happens there? Yeah, it goes from being a negative number, maybe even a small negative number, to being a big positive number, and that's not right. So you're going to see that there's an additional guy called SRA, shift right arithmetic, that kind of sign fills it. Whatever the high sign was, preserves it. So preserves the sign value of that. So that's kind of nice. So there's SLL, SRL, and SRA, which are useful to move things around. And you're going to see why that's useful. Next slide. Yeah? Okay. So we're still working on doing conversion of C to MIPS. We're still in the model of C to stank C to then, C with go-tos and labels to then MIPS. We always have known that's the way to do that. So here's my do-while loop. This is a very simple do-while loop. G equals G plus A of I equals I plus J, and while I is not equal to H. Very common piece of code. You might see this all around. You rewrite this as stank C, which is here's a label, here's a go-to. And you can see why this is the same thing. Let's verify that. Do means do the stuff before you even do the test the first iteration. And then do the test and keep going as long as the test is still true. So it says loop, and then do code, and then if this thing is true, then go back to the top. It actually reads better as the stank C than it does in the do while thing, just in terms of parsing it if you're new to C. So now, assuming this is our mapping and it's a little dark, base of A is S5, how does this work? Let's walk through. I'm not going to make you do this. This is a little harder. But let's actually walk through together, make sure every line, in fact, I'm going to sit in Mike's chair, I'm going to join you as an audience member, and let's now appreciate this together. Here we go. First line, SLL, SLL. Dan just taught me SLL. This is why I needed that before, because I'm going to be shifting over. Why? Why am I, let's all react. Why am I doing an SLL here? Look at this. Remember the comments I say are often more useful than the thing. T1 equals 4 times I. Here's the code right here, right? I need to get to the A of I. I'm trying to get A of I, and then add it to G. G is an S1. Here's my final G equals G plus A of I. So T1 is going to be the temporary guy storing A of I. So far, so good? Say yes. Okay. So now, how do I get A of I? A, I didn't tell you, is an array of integers. Okay. Well, too near a cell phone. That's what. See what? No, I touched it. See how when I touched it? That's the. I have to go away from. No. There's this great, hilarious movie in 1978 called The Jerk by Steve Martin, and he thinks that some guy's trying to kill him, and he has this, and he's running, and he keeps thinking the cans, because he stands in front of these cans, and the sniper is shooting at him, and he keeps the bullet holes go and the cans are like exploding. And he's like, it's the cans. He works at a gas station. He runs over here, and all of a sudden the guy's trying to shoot him some more, and then and he goes, more cans! It's the cans! So now I'm saying it's the cell phones. Okay, so it's the cell phones. Like I could actually get away from cell phones in today's society, right? So maybe it's me. I wonder if it actually is me. Look at that. I'm going to turn my cell phones off, and maybe that's going to help. Okay. So let's go back here. T of I equals 4 times I. Why am I doing this? Well, Dan, for like the 9th lecture in a row, you're reminding us that when you have it's byte addressed, but integers are 4 bytes wide. When you go to the next integer, you have to multiply by 4. If I go to A of 5, it's actually the 20th byte away from A. Remember that last time? So something has to multiply by 4. So let's do this. Look at this. Shift left logical, T1, S3, 2. S3 is the red guy, which is the I. So now I times 4. T1 is I times 4. It says it here. Then I add that unsigned. Now the first time you're seeing unsigned because it's an address. Why would I have a signed thing that if it happens to A, it better not wrap. If it wraps, then I've like read off the edge of the A, which is possible. You could have an array that starts at the top and only have like a couple bytes, but you put in an argument of A of I of A of 300, and it actually would be something past your address space, which will wrap. But it's C, you should make it fast. So if it wraps, I don't care. The segfault will cause an error in the first place, right? So anyway, it's actually curious that this could actually work. If you call this add U, and that index is big enough, it could actually wrap you to a valid place that is word aligned down here, and you're now reading from a thing down here rather than anyway. So TI equals address A plus 4I. Remember, the 4 is going to come and bite you over and over and over again. So this is how cool the SLL is. It says I, shift left by 2 spaces. Now it's I times 4. I add that to my array, put that some temp guy called T1 with no offset, and that's how you access A of I. You may have not seen how to do A of I in general. You said, like, Dan, I get this thing here, and people after lecture on Friday said, when do I ever have a non-zero number as my offset? And I say, well, sometimes in structs, and sometimes if you have hard-coded A of 5, you'd put 20, as we saw in the other example. But here's a case where you have A of I, which you're going to, the most common thing in the world is A of I, right? That's the most common thing in the world if they're going to take your memory. And so this is how A of I gets translated. It takes 4 lines to do A of I. 3 lines for A of I, and the addition is the 4th line. Questions about that? Hopefully, it's just, I went a long time on something that isn't that hard. Then this is I because I plus j, and then this is branch not equal. If I is not equal to h, which is these guys not equal, go to loop. Branch not equal, go to loop. I'm done. So these 3 lines became 6 lines of MIPS, but hopefully not too bad. Questions? All right? Okay. So one of the things to note is that now that I have given you how to do a do while, you recognize that essentially these while, do while, for all can be kind of rewritten as each other. So in fact, now you could do all of them, right? It's now an exercise for the reader how to convert a for loop into this stuff with the branch not equal and the testing and the labels and the go-tos and that stuff. But it isn't that hard. Okay, so now in theory, you could actually hand compile any of those things over and feel very confident with that. And again, the key thing here is the conditional branch, the BNE, the BEQ. Okay? So now we're closing out on how to do that. Administrivia. We had a really great TA meeting. We felt so good about this. We have planned out everything up and through. This is all, remember, a new class for all of us. I think one of the TA, I think Ryan has been familiar with discussed before, but for most of us, this New World C is new for us, and so we're kind of trying to make sure that we have it a couple weeks in advance, and now we're week 4 today with us, but we have the schedule confirmed and finalized up through week 7. And we feel really good about that, including the midterm being scheduled 7 to 9 p.m., giving you enough time for dinner and coming back and doing this thing. Not a 3-hour exam, just a 2-hour exam. We're going to write it for it's less than an hour. I'm going to make sure my TAs can do this midterm in less than an hour, but we give you guys 2 hours for it on the 6th of October. Other administrivia that I'm forgetting, we've hired all our readers. The readers are going to be, they're awesome guys. We blessed that. So we're going to have your readers giving you your stuff back. We're excited about that. And yes? The midterm is going to be a cheat sheet. It's a single sheet of paper, handwritten on both sides, as it always is in 61C. Other TA things, we're set on Lab 20, which is now 330 soda. Anything else outside of TA? We have, if you know anybody who's taken 61C, tell them to come join us on the team of lab assistants, right? If you got an A or a B, which is like, the vast majority of the folks who take 61C, tell them there's a lot of room for lab assistant help. Basically, anybody who's coming up to us, we're saying you get the job. So anybody who comes up to us, please let them know that there's opportunities for lab assistants to help you out. That way it's not just one TA like running around like a chicken with the head cut off trying to get you all checked off. Okay, so now you're saying, Dan, I like it. You've got this great BNE, BEQ thing, but the world isn't so simple for equality and inequality, there's also like greater than or less than issues. So how do we do that? So for the next couple of slides, we'll talk about that one. So there's this cool thing which I'm going to add, which is SLT. It follows the register, register, register format of adds. So that's actually pretty easy. And what it does is sets the lowest bit of the leftmost argument, and here is reg1, to be a 1 or a 0, depending on whether reg2 is less than reg3. And the reason that is set means change to 1, and reset means change to 0. You may have never heard about it before. It's an interesting thing. This is the first, all double E's know this. The idea of a set on a signal line means set it to 1. Like set the clock, which has more semantics stuff, but set the light means turn the light on. Reset the light means turn the light off. That's like the double E way of thinking about it. So when we're talking about this, set comes from that double E mentality to make it 0 or 1. So this is the line of C code. If you're familiar with reading C code, the expression is calculated. If it's true, the result is a 1. If it's false, the result is a 0. And then register 1 is set to either a 1 or a 0. That's all it is. The upper 31 bits are ignored because they're always set to 0, never changed as a function of the arguments. The lowest bit we care about. And we're going to show you how to mask that out and query that and all that stuff. And you already can think to yourself, those of you who are smart can say, oh wait, Dan told us about this cool register called $0, and comparing against $0 is very useful here. Now you say, oh, remember you said you'll thank me for giving you a $0? You can already see the next slide coming up that I can now compare that reg1 with $0 to see whether that's true or not. Does that make sense? That's going to be very useful. Okay, questions about SLT? So now, this is the same thing as this code right here. Reg1 is 0, else reg1 is 0. Reg1 is 1, otherwise reg1 is 0. Same as the green guy. So, here, look at this code here. So this guy says, how do we do if G is less than H, go to less? And here is a solution. G is less than H becomes S0 less than S1, if I have G and H be those guys, okay? I set a temporary guy to be T0. It's not easy to have this done without a temporary variable. I usually have to have a temporary register to have that the storage location for the 1 or the 0 that's going to be a result of that. And then I branch if not equal to 0. And I was thinking about a way to teach this, and I came up with a new way to do it, which is branch not equal to 0. It's only set not equal to 0 if that's less than that, if S0 is less than that. So I think of these two combining to be BLT. I just thought how clever that was. Okay, so because it's like branch if this is true. It's true if it's not equal to 0, which means that was set to 1, which means it's less than. So think of a BNE, of an SLT BNE combination actually being a BLT. Branch if less than. And now I'm branching to less if S0 is less than there, which is exactly like that. It actually reads like that. Branch if less than. Go to less if less than. BLT. Love it, right? So think of the BNE, SLT BNE combination becoming the if go to and becoming a BLT. Okay? Good stuff. So we can do that. So remember, we're minimalists, right? So let's think out loud. If we're minimalist MIPS people, we want to introduce the fewest number of additional instructions to be able to let you convert every C code ever to MIPS. So I'm sitting here, I have less than. Well, obviously, I have to then have 3 more. Whenever you have less than, there's always 3 more. There's less than, there's a family of them, right? There's less than, there's greater than, there's less than or equal to, there's greater than or equal to. A family of 4. They come as a package of 4. I have to have 4 place settings around the table, right? I must have to have 4 other instructions that I unfortunately have to have you know about and implement and all that, right? Ah, smart people. How can I get away with fewer than 4? In fact, while I'm here, let me throw this wonderful puzzle at you, and I'll see how many of you can do this one before the next time I say. You go to a party. I still have time, yes. You go to a dinner party, and this is an aside, a 30-second aside. You go to a dinner party, and you're a genealogist, and you want to invite the fewest people. And what you have the power of doing is manipulating your family tree, so you can have anybody marry anybody, but don't have cousins marry. You can't have relatives marry in an uncool way, okay? But you can basically have like 2 brothers marry 2 sisters or something like that. That's legal. You can do that, right? So you want to be able to invite the following people to this dinner. the brother's father-in-law, the brother-in-law's father, the father's brother-in-law, the father-in-law's brother. Okay, all the four combinations of brother, father, flipping around and saying in-law. Okay? But you are cheapskate. You don't want to have to invite 4 people. Can you manipulate the family tree to have that be fewer than 4 different people? That's an aside, fun puzzle. Think about it. Same as this. Same idea, right? I have to have 4 different MIPS things, right? No, you say no. Somebody give me some love. How can I save my space? But don't read the answers which are in the slides. Who can not look down and tell me how I can save having to think about and implement additional MIPS instructions? Yeah, do you have it going? Give me what's your name? Yang. Go ahead.
Can you swap the last 2 arguments?
Oh, I like it. On which one? On B and E? No. On SLT. So swap S0 and S1, and what's that actually doing now? SGE. The opposite. So if it's not less than, what's the answer? Like logically, let's go back to logic. If it's not less than, what does that mean it must be? Greater than or equal to. So now I've got my pair. By just swapping those 2 guys, I've now got greater than or equal to. Love it. You got that? Okay. How is that it? So now I can reduce 4 to 2. No, to now I've taken 1 away. But I still have 2 more guys. I got it. What else? What other fluidity do I have? Yes, in the back. What's your name? Adif. Go ahead. Give me. Steve, go ahead. Sorry, go. Sorry, I didn't get the name. It's hard to hear. The second line. Yeah, I have a second line to play with. I love it. Change the BNE to be BEQ, and that's the other one. Right? So, actually, let me go back. I think you were giving me greater than. You didn't do that was the opposite. The whole not thing I did was actually the thing that this gentleman just said. Right? If I swap the BNE to BEQ, it is greater than or equal to. So that's the one that gives me greater than or equal to. I think I kind of got myself tripped up. If I just swap the first 2, it's just less than or greater than. If I swap the bottom one, it swaps the logical part of it, which is the not part of it. So anyway, I have some slides describing it because I think I did a bad job of saying it. Now I've implemented less than. Can I do the other 4, or the other 3? And the idea is here, 2 independent variations allow me to have SLT S1 S0 instead of SLT S0 S1 and BNE instead of BEQ to get all the 4 combinations and just think about which one you need for that case. Okay? Swapping the top just changes from less than to greater than. Swapping the bottom does the negation of that. So a less than becomes a greater than or equal to, or a greater than becomes a less than or equal to. I think I said it right just then. Okay? Good stuff. Not too hard. Now let's do immediate. So now you're saying, Dan, that's interesting. I can do register comparison, but I have no way to compare whether I'm less than 10. If C is less than 10, do something. How do I do that? I don't, actually. I can do less than 0, because I can put a register 0, but I can't do less than... Yeah, question?
If you just move it into a register?
How do you move it in a number into a register?
Add immediate.
There it is. So I could. Excellent. So what I like about this, the answer is, you actually have all the power to do it now. I have an immediate, which I can say, add IU probably, well, it doesn't matter, right? Destination register I care about, 0, and some constant. And now that's really like taking a number and stuffing a register. And I compare it in that nice way. I could do that. And in fact, at the pure minimalist sense, I don't need anything else. I really should live with that world and understand that I can build that. But they say, that's comparing it to register is enough that the trade-off of making a purely minimalist MIPS and then having every comparison be 2 lines is done too often. So they're going to want to actually give you a direct. It's just like a trade-off where, in theory, the purist would not do that. Would say, "You're done. I can handle it already." But we're going to actually add another guy because it's useful. So in for loops, we do it so often. You want to be able to not have to have 2 guys for every check against a constant. So I'm going to have SLT and SLTI. So SLTI is the cousin of SLT to set for that. So if G is greater than or equal to 1, go to loop. So what's the MIPS for that? Don't look down. Let's see if we can do it. G greater than or equal to 1, go to loop. We can start with SLTI, some temp guy, G, and 1. And that's testing whether G is less than 1, and then setting some temp guy to remember that, okay? What will we do next? Now I know whether it's less than 1, but I really want to know if it's greater or equal to 1. BEQ or BNE? If it's false, would be BEQ, right? BEQ, temp guy, 0, loop. SLTI, BEQ, well done. So, this might be hard for you now. You do about 5 of these and you'll get it. It's really not that bad in terms of knowing how to translate the less than into this. Just be careful though. You don't want to mess this up on exam. Just, take another second to check your work to make sure you're doing the right parity of that. Yes, question.
How do you do greater than? Because you can swap arguments here.
I love it. That's a very good point. What's your name again?
Rohan.
Rohil. Excellent. That's the second time you asked the best question so far. You can't do this. I always wait to ask. Every year, it's so fun. I set these traps, which is, it's like somebody gets it that you can't swap the right arguments anymore because the rightmost argument has to be a constant. You've never seen a pattern which is register, constant register. You've never seen that. So you know that the constant has to be on the right, so how do you do that? What do you think? If you can't swap them, then how do you handle the other case? You can swap the BEQ and BNE. You can still swap that guy. So you can do here greater than or equal to, and you can also do less than. But you can't do greater than or less than or equal to. So you got to make a new instruction. What would that be? Set on greater than. Right? That's the flip of it. So you have to make that extra instruction to make that, unfortunately, because of the way the format is. And you can't just swap these two arguments here. Okay? You don't know that you can't swap the two arguments. That's actually going to be the next lecture. Starting on Wednesday, I'm actually going to reveal to you how these map to ones and zeros. We're going to kind of put this stuff on hold for a second. I haven't really told you how to make function calls yet, and how to have recursion, all that stuff. That will put on hold for a moment. I'm going to show you how the ones and zeros work so that you can work on your homework to do that. So, actually, it's the project I did that for. Yes, question? Yes. You can. As I said, you don't need to have SLTI because you could just take the constant, put it into a register, and then use all the stuff you had from 3 slides ago. But correct. We're already not being we're already giving up the MIPS minimalist because we added SLTI. So while we're at it, the wallet's out. Yeah, treat me and treat the whole house. Let's buy everything and let's have an SGTI also. All right, so now you're going to say, Dan, this is the 3rd time today where the word unsigned has come up, which is, so far you saw, do you sign, extend, or not? That's the LB or LBU. Do you do overflow detecting or not? That's the addu versus the add. This is the 3rd time where the U is coming into effect. If I'm comparing two numbers, which is bigger? I have one number with all ones and one number with all zeros. Which is bigger? Your answer better be depends. If you say the ones is bigger than the zero, I said, oh really? In signed representation, where all ones is -1 and all zeros is 0? Oh really? So isn't that a sign of life thing? Really? Right? So what we do here is we have to know how we're treating our arguments. As I said before, and you've seen now multiple times, there's no way of kind of attaching a label, and put a post-it, that register is a signed guy, and this one is a float, and this is 4 characters. You can't do it. You have to remember that. If you're hand authoring code, you got to remember that. Put the post-it for your brain. If you're a compiler, keep some additional data structure so you know what is what. The only guy that knows that is the operator. If the operator is doing a sign comparison, if it's doing a comparison of less than, it better assume SLT, the U means the unsigned. So by default, when you don't see a U, you mean signed. So by default, it's just an int. you're comparing two integers which are signed integers. You have to say the word unsigned int to explicitly mean unsigned numbers. But in general, we do negatives and positives together. We do the whole gamut. So here's a number with a lot of ones at the head. Here's a number with a lot of zeros in the first nibble. It's not just first nibbles, first four nibbles. Each of these guys is this is 32 bits wide. So here is my question: which is bigger? What's the value of T1, T0, and T1? Well, I don't want you to have to do it in real time, but this is a lot of ones over here, which is either a big number, unsigned, or a negative number in signed. And this is either, actually this guy is the same. The guy on the right is the same either way, because if you lead with 0, then that's unsigned and signed are the same values. So this is a small number, less than 16,000 or so. I think that's it. So you need the unsigned if you're going to do the unsigned comparison, and the signed if you're going to do a signed comparison. That's it. So now, this is the summary slide about the overloading of the idea of being unsigned. Unsigned has 3 different meanings. You either are loading a byte from memory, and you need to be able to sign extend or not, and that's the LB versus LBU. You either are doing an addition and either detecting an overflow or not, and that's the add versus addu. And you either are doing a comparison, treating the number as signed numbers when you're comparing which is bigger or smaller, or unsigned numbers comparing bigger or smaller, and that's the SLT, SLTI versus SLTU, SLTIU. Okay, questions about that? This lecture, what's funny about this lecture is really kind of a potpourri of all the things I forgot to say. Not me forgetting, but like things that just don't get said in the narrative of teaching you MIPS. There's a lot of small pieces that you get. Here's some unbind, here's some shifting, here's some other stuff. This is just kind of rounding out the things that we kind of didn't cover in the main thrust. All right, questions? This is not that bad a lecture. So, this is the fun one. Can you do this tricky, maybe not tricky, hard, maybe easy puzzle? I have the following code. Do I minus minus while blank. And what code properly fills in the blank of all these options in the loop below? So here's the code. And you can really, to be honest, read the gray comments, because the gray comments are correct, and maybe the gray comments help you. This is one of those cases where actually reading the comments is faster than reading the MIPS and try to crack that one. So be quiet, and let's see if I can actually get you to honestly do this one. This is a real question. Starting to get more towards what I ask you in a midterm, but again, this is still on the easy side because you're still learning this stuff. But this is the kind of thing that we would ask you to do. I'll move this over here. I think, hey, move over. Wake up there. Okay, move over to there. Okay. So think about that as your process. Don't talk until everybody votes in if you can. All right, talk to your neighbors. If you haven't voted, still think about it and vote in. But figure out what you can have for that. Most of you had it right, so let's vote in quick again if you can, since this wasn't too bad a question for most of you. So wait till it wakes up again and receives it. And action. There we go. It does queue it up, which is quite nice. So 50 votes, it went from 0 to 50 because it remembered that. And this is a pretty easy one. I'll stop it now. You guys are getting this pretty well. Anybody want to tell us what the right answer is? If you think you're pretty confident? Who hasn't spoken yet? You're probably right. 83% of you said the right answer. Go ahead. Sure. Yeah, go ahead. Jojo. Which one? D. Why is it D? It's an or because either one of them could have jumped. Either both chances to go back to loop. That's right. It is an or. Right, so this one, an SLT BEQ is the opposite, so it's actually greater than or equal to 2, and the second one is an SLT BNE. Remember I said SLT BNE becomes a BLT, and that's just a J less than I, so that's a D, which is, I guess, this right in here. Good stuff. So just to show you guys all did pretty well on that one. That was too easy. Okay, so we just had homework to do, right? How many? I love that, right? So watch this. Watch this. It's called a question on the fly. Okay? How many hours on homework 2? A, 0 to 5, 0 less than T less than or equal to 5. B, 5, is the 5 the right unit? Maybe I'll just try it. I'll hope it. 5 is that. T less than or equal to 10. C, 10, T, 15, D, 15, T, 20, E, okay, shh. And I will let you vote and watch it as it comes up. I love these things. Sorry? I didn't hear. Oh, it's not finished. You're still working on it. You're doing slip days or something? Okay. Start. So maybe 5 was the right unit, I guess. Wow. Okay. So most of you are getting it in another 10 hours. I'm pleased with that. Roughly, just to give you a sanity check on this, roughly every course at the 4-unit course is a 12-hour-a-week commitment, and I believe you're spending, how many is it, 3 and 2, 6 hours with me. Does that sound right? 3 lecture, 2 lab, 1 discussion, that's 6 hours with me. So that's roughly 6 hours a week you should be spending on outside homework. from this class. So ideally, 6 is the right number. That's what's supposed to happen. If it's more than 6, we're overworking you. And guess what? We're overworking you. All right. So anyway, thank you for that feedback. That's why we make projects, which are big, 2-week things, right? Because it's more than 6 hours each. It's a 12-hour project, okay? We'll see you guys on Wednesday. Have a good day. Enjoy the weather.